For the next panel, we will go in the medical world with Ninon Burgos and Laure Fournier with medical imaging. So Ninon is a CNRS researcher at the Paris Brain Institute in the Aramis lab. She is a holder of a PRAIRIE chair. She completed a PhD at University College London. And in 2019, she received the RCIM Core Bayern Young Award Researcher, which is awarded each year to a promising young researcher in computer science or applied mathematics. Laure Fournier is professor of radiology at Hôpital Européen Georges Pompidou and Université de Paris, and also holder of a PRAIRIE chair. She's member of the working group on artificial intelligence for the College of Radiology in France. She's member of the Society of Radiology, and she's conducting a lot of work mixing radiology, medicine, and AI. So just to start, today AI is present in all the fields of health, but now today we will speak about imaging. This can be a decision support. So my first question will be for both of you, how has AI changed the way you work, in a few words?
Well, I will start. Thank you, Isabelle, for the introduction. Until the deep learning boom in the medical image computing community, we all had our specialty. So some were specialized in, for example, the reconstruction of images, some in processing such as segmentation or registration, and some were focusing on classification for computer-aided diagnosis. But now the borders between these areas are not so clear because deep learning can be an answer to each of these questions. So I think people now tend to move more and more from like one domain to the others. And so this change a bit like the way we work because we can switch more easily. And all this became like a more maybe unified, but because we all work with the same type of methods, but still, I think we still need our specialty because we really have to tailor these methods to our specific needs. So it changed a bit, but not entirely the way we work.
So thank you, Laure.
Yeah, I agree completely with what Ninon said. In some ways, the way we do research has not changed. I mean, we've been extracting information from medical images for years, and we've been having trouble with data. We've been having trouble generalizing our solutions to other institutions, even correlating it to biological mechanisms. So these are kind of similar problems, but what has really changed, I would say, is first of all, AI has really made solving some of the issues a realistic goal. That means there were things that we were having trouble with and that were just not giving us useful solutions, and the at least neural networks has made these possible. Also, it's attracted to medical imaging people from very diverse fields. People from computer vision outside medical fields are interested in medical images now, data scientists. And then finally, I would say in my field, and that's something I'm very happy about, is that it's brought back towards research people who had sort of given up on research because it was too difficult. Med students, residents, even private practice physicians. And I think that's giving us a diversity, and it's making research kind of cool.
Thank you. I think you have prepared some example for us. So maybe starting with Ninon.
Yep. Okay, so I'll actually start with something you should be familiar with, which is the ImageNet challenge. And one of the tasks of this challenge is to classify natural images. And what you can see on the graph is how deep learning, first with AlexNet, managed to drastically decrease the classification error compared to more traditional machine learning approaches until it finally surpassed human performance. And when we saw that in the medical imaging community, of course, we wanted to apply this type of methods to our domain. So in my case, we apply them in the context of the computer-aided diagnosis of Alzheimer's disease. Here we take as input a magnetic resonance image, so an MR image, and teach the network to distinguish cognitively normal subjects from patients with Alzheimer's disease. So we started quite naturally with a review of the literature, because it's what we do. And so we targeted articles published in journals and recent conferences that used convolutional neural networks and were based just on structural MR images. So we looked at the performance they obtain, at the type of approaches that were used, and we also quickly became interested in how the methods were validated. And we had some surprises here, because in half of the cases, we found potential data leakage problems, meaning that the data were used both to train an approach and to test it, which really creates a lot of bias. And so we have classified these articles into 3 categories. So clear, that you see in red, when the data leakage was explicitly mentioned. Unclear in orange, when there was too little information to actually be sure that the method was validated properly. And green, when no data leakage was detected. And we found, not surprisingly, that performance was much higher for articles with potential data leakage. And so because of the flaws of the validation of many articles, it's impossible to compare approaches and so to draw conclusions regarding the strategies that work best. And so our first objective then was to develop a framework that allows us to rigorously compare various approaches and to identify the factors such as, for example, different image processing or different network architectures that influence the most the accuracy of classification. So this framework is called Clinica-DL, and it is a result of the association between Clinica, which is an open source software platform that we develop in the team for neuroimaging clinical studies, and the PyTorch library, which is dedicated mainly to deep learning. And so Clinica-DL's functionalities are centered on the use of deep learning for image classification. And so the platform reuses Clinica's image processing pipelines and offer unique features such as neural network training and inference from trained models. And so thanks to this framework, we perform many experiments. And for example, we compare the results obtained on different data sets and different classification tasks. These results obtained with deep learning methods and traditional machine learning methods. And we found that basically they give pretty much equivalent results, so here balance accuracies. But it's not excluded that more sophisticated deep learning methods may offer higher performance, and it's actually the same for machine learning methods. I think here just a take-home message is that with the often limited number of samples that we have to train, machine learning methods shouldn't be discarded. So deep learning may not necessarily outperform traditional machine learning when performing classification, but it could bring new insights. And so here we're not only interested in the label given, here Alzheimer's disease, for example, but based on what the network came up with these labels. And so because we work with images of the image, I mean, what part did the network use to answer? And so to obtain this answer, the idea is to mask the minimal part of the image that is necessary to confuse the network. So if we take a simple example, let's say the objective is to identify the presence of the flute in an image, so to classify flutes. If we mask the flute, then the network cannot recognize it anymore and cannot say that this image contains a flute. And so in the context of Alzheimer's disease, we can obtain this mask at the level of the group, so and have a general pattern that characterizes the diseases, here Alzheimer's, for the convolutional network. But we can also obtain them at the individual level. And here it may be possible to then study individual differences. And this is actually the line of research that we are pursuing. So yeah, this was my example.
Laure had some examples too, in the radiologist's point of view, sorry.
Yes, I do. I wanted to talk about some work we did with one of my master students, who is called Victoire Roblot. And it's actually for a task, it's actually using deep neural networks for a task which is called segmentation. That means delineation of anatomical structures in an image for quantification of what we call sarcopenia, and I'll explain what that is in cancer patients. So the idea behind that is that we usually perform imaging, for example, to diagnose a cancer, sometimes also to see if a therapy that is given to a cancer patient, if it's working. And of course, imaging is very useful in that case. But on the right, I sort of depicted a group of patients that all have the same disease and that we think are all the same. But actually, patients can be different. They might be different because they have different family or personal histories. They might be different because they have what we call comorbidities. That means other diseases that might impact how well they will react to therapy. And so actually we have a very diverse population. And what's interesting is that in images, we can pull out information about this diversity. We can learn about the cardiovascular status of a patient by looking at his heart and the heart vessels. We can learn about his nutritional status, and that's what sarcopenia is about. And this middle image shows the delineation of the muscles in the abdominal wall of a patient, which reflects how the nutritional status of a patient. And all this is present in the image, but actually on a day-to-day practice, it takes a lot of time if we want to quantify every single one of these features. We are moving to what we call holistic imaging or global imaging of patients, which means that we should be able to mine that wealth of information that's present in all the images on each individual patient. What is sarcopenia and why did we work on this? Well, what actually happens is that when a patient has a cancer, he's going to undergo weight loss. And it's not so much of a problem if it's fat loss, but it's a problem if it's muscle loss, because that actually shows a bad nutritional state. And when these patients have this sarcopenia or muscle loss, well, the therapies will be less efficient and they will have more side effects, which will actually kind of promote the cancer in evolving, which will once again induce muscle loss. And so you enter this vicious circle. So what would be perfect is if we could tell the oncologist at the start whether the patient has a good or a bad nutritional state, and he could put together a dietary program to kind of break that cycle. The problem is, as I was saying, if we had to quantify everything every day in our clinical workflow, and it would be very time consuming. And so in data to practice, we never do it. So we wanted to know if we could have help, if we could use AI tools to help us. So my master students, Victoire, actually worked first on a training set, which comes from a data challenge that the French Radiology Society organizes every year. And last year it was on sarcopenia. So in this training set, there were over 1,000 patients where radiologists had manually delineated the muscles. And they trained an algorithm with cross-validation. And then we put together two validation sets, well, two external sets, one for validation compared to manual segmentations, and then a test set. What we used was a convolutional network based on DeepLab, which is an ATRU convolution with a ResNet backbone, and also there was loss weight that was added to that. I'm not going to go into the detail, but I'm just going to show you the results. So if you're not used to these graphs, which we use a lot in oncology. These graphs are called survival curves. So they show how well patients survive beyond the diagnosis of their cancer. And what you can see here on the left, this is when we use manual segmentation. So radiologists who delineate on the images, you can see the patients who have sarcopenia, so they have muscle loss, this is the blue line, have a worse survival, so worse prognosis than the ones that have a good nutritional status with the orange line. And what was interesting is that in both our external data sets, using our deep learning based tool, we could separate these two prognostic groups just as well as the manual segmentation. And this is very important because we want our tools to be useful for the oncologist. So if I summarize, the idea behind this is that when we have this large group of cancer patients that all have the same cancer and for which we would think that they would all react the same, well, we have developed a tool that we could incorporate in the workflow that would not be time consuming because it's the deep learning network that does all the work, and which would separate patients that don't have sarcopenia and have a rather better prognosis from the patients that do have sarcopenia, which would allow then the oncologist to give them a special diet and try to bring them back in that good prognostic group. So this was just an example of a very simple tool that could actually really change the way we take care of patients.
And powerful new tools. But with this, what about accountability when AI is used in decision-making process? Who wants to start?
I can. For example, the interpretability methods that I show you an example of in the presentation, they can be used in the development process to just for like sanity checks. First, just to see that we are, because for example, if for the diagnosis of Alzheimer's, the part of the image that I highlight is the background, then I know that I'm not basing my decision on something that makes sense. And so this is a way, for example, that we can ensure that the methods are making sense. Another tool would be to use uncertainty. So to compute uncertainty, for example, for segmentation methods, where here you're able to say, oh, in this part of the image, I'm not sure of my segmentation. The network is not sure, and so then we can give that information to the person in charge of making a decision. But the decision should always be in the hands of the clinician and not in the hands of the methods, basically. I don't know if Laure, you agree with that.
Yes, of course, I agree. I think human validation is important because there are so many important decisions that are going to come out of these tools. So I think the example I showed was, I chose that on purpose so that I would show an example that was kind of simple to control. I think it is important that we develop tools that will show the result from the network so that we can check visually, at least, that it's coherent. Of course, it has to be correctly integrated. It will be a bit more difficult when the network will pull out features that we aren't able to control visually. So what I'm sort of expecting from the data scientist specialists, what I would love is at least to have a network that tells me this image is completely different from what I've seen before. So just be careful with what I'm saying, or I'm not analyzing it. I think that would be a pretty good start to make sure that we don't make decisions that we can't back up.
So thank you. One word of conclusion, maybe from Laure. Do you face challenges to make your innovations be accepted in practice?
Well, yes, I think these have to be accepted both by the patients and by the physicians. And even though everyone is fascinated about this, there's also a bit of people are a bit worried about what it actually means. So I think we just have to start using them, put together those techniques to just control the result, and little by little we'll understand how to use them better.
thank you. This is a nice conclusion. So thank you, Laure. Thank you, Ninon. And thank you for the audience, to the audience.